mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning, calculus class. It's good to be back and to see you again. And well, not see you physically, but you can see me at least. We're going to continue on in our calculus lessons, and we're remembering that we're in our applications of derivatives units, and we're actually coming close to the end of it, and so there'll be some kind of assessment coming up. You can watch for details on that. Since this is a calculus class, while I didn't bring a snack to class today, I did bring a coffee, and a little shout out to A&W. Very good coffee this morning, and I will be taking sips of that periodically throughout the day today. This will be your only video lesson of the week, as we are into our last application, which is called related rates. And related rates is probably the most complicated thing, and it's a area where the questions are I won't say infinite, but they're close to infinite. We can ask all kinds of questions that deal with related rates. And basically what a related rate problem is that we're given one quantity that is changing with respect to time and asked to find a different quantity that is being changed with respect to time. So we'll do a question today momentarily about a snowball melting. And as a snowball melts, two things are changing with respect to time. The circumference is changing and the radius is changing, which also means the volume is changing and the surface area is changing. Right? So all kinds of things are changing with respect to time. And so we'll be given one of those quantities that's changing with respect to time. Say the radius is shrinking at a rate of whatever it is. And then what is the circumference shrinking by with respect to time? And so we'll be looking at questions like that. Another classic example is a pool being filled with water. As water is being pumped into a pool at a certain rate, what is the rate that the height of the water in the pool is changing at? All right, so those are classic kinds of questions, and we need a method to solve them. Now, because we're doing questions with respect to time, we have to use our implicit differentiation skills. Remember when we did implicit differentiation, when we had formulas, equations that couldn't be solved explicitly for y, we had to leave the equation the way it was and we had to implicitly differentiate, which meant we differentiated the values of x normally, as the way we did just using a power rule. And when we had variables of y, we treated that as if y was a function of x, and we differentiated those terms with y implicitly. And so now what we're going to do is, because now we're doing everything with respect to time in a related rate question, both variables are changing with respect to time, and so both variables will get implicitly differentiated with respect to time. And so we'll be using the Leibniz notation of dx over dt, or dy over dt, or whatever the variable is, over dt, so that we are going with respect to time. On Connect, I'm going to put this paper. I know you can't see it. That's okay. It'll be on Connect. It is a steps sheet, similar to the steps sheet that I put on yesterday for optimization problems. We've got steps for related rate problems. I'm just going to read them to you. I'm not going to write them down. And you'll have them on your Connect page. And then as we do the examples, we're going to go through these steps. And today I'm going to go through 4 examples using these steps. And then I'm going to give you a lengthy assignment that you'll find on Connect as well. And that assignment we'll work on all week long and into next week, because it's lengthy. And the questions are difficult. You will have to struggle with them. You'll have to try them more than once probably. And I want you to persevere, and I want you to try them, and I want you to really, really put some effort into these questions, as they are the real world questions, and they were the ones that are applicable to things. And so let's get at it. So the guidelines are simple. There's 6 of them, okay? And we'll go through them as we do an example in a minute. So it's step 1, read the problem carefully several times. Make sure you understand what the question is asking. Make sure you know what's given and what needs to be found. Okay, and you see on the board behind me here, I've already written down some things here for the first example about what we have and what we're supposed to find. All right, so that's a good practice to get into. Understand the question, know what you have and what you need to find. Okay. Part 2, sketch a picture or a diagram and label it appropriately if necessary. Okay, this first example we're going to do doesn't have a diagram. We're not going to draw a diagram, but every other one after that will have somewhat of a diagram. And because it's a word problem, you get to introduce the variables. Now the variables will be simple. Right, if we're looking at volume, we're going to use V for volume, radius, R for radius. Right, so you'll introduce the variables just so that you know what variables you're talking about. Okay. So you're going to introduce your variables. Okay, again, you're going to write down your known facts and express your unknown rates as derivatives. Okay, so you'll see here too, anytime I have a dx dt, that's a derivative. Okay, here I have a dy dt, that's a derivative. Okay, so we want to find a derivative with respect to time, and we're given a derivative with respect to time. Okay, step 4. Formulate a general equation that relates the variables. So again, this first question, I'm just giving you an equation that we're going to differentiate. All the other ones will be problems where we won't be given a formula. So if we're looking at a sphere, a snowball melting, depending on what we're looking at, if we're looking at volume and radius, we need a formula that has volume and radius in it. All right, and so I'll provide again on Connect a little bit of a formula sheet that has some basic shapes on it. It'll have their volume formulas and surface area formulas, and you can look them up if you need to. Okay, step 5, differentiate the equation. So once you've got the equation, now you need to differentiate it with respect to time. Okay, and once you have the derivative, then you should be able to put in your known quantities and find your unknown quantities. Okay, and as always, when you get to the end of a question, make sure you check to make sure your answers make sense and they work in the question, that they fit in the domain of the question. All right, let's do a few examples and hopefully it will become a little bit clearer. I'm not going to write out the examples, but I'm going to read them to you and then we'll draw the pictures and do it. So if you need to write them down, you can rewind me as much as you want and listen to this over and over and over again to get the questions. All right, so this first question on the board behind me, pause for coffee break. The first question behind me simply states, 2 variables, x and y, are functions of time and are related by this equation, x cubed minus 2y squared plus 5x equals 16. If dx dt equals to 4, when x equals to 2 and y equals to -1, find dy dt. So this is not a real world situation necessarily, this is just a question. Okay, here's a formula, differentiate it with respect to time. All right, if we're differentiating with respect to time, that means we're treating both x and y as a function of time, and we are going to differentiate implicitly. Okay, and here's where we're going to use the Leibniz notation, which is that dx over dt, or dy over dt instead of x primed and y primed. Okay, so here we go. If I'm going to treat this, I'm going to start by taking the chain rule, sorry, not chain rule, the chain rule, and using power rule within that. So I'm going to multiply the 3 out front, I'm going to get 3x squared, and then I'm going to take the derivative of x with respect to time. So times dx dt. Okay, and that's the derivative of 3x cubed, of x cubed. Minus, now we're going to take the derivative of 2y squared. Again, we start by multiplying the exponent out front, reducing it by 1, times the derivative of y, which again, with respect to t, becomes dy over dt. Okay, plus, again, here, we're treating 5x as a function with respect to time. Now we're going to do it implicitly, which means, again, we have an exponent of 1. We're going to multiply it out front, reduce it by 1, it becomes x to the 0, which we don't write down, times the derivative of x with respect to time, which is dx dt, equals the derivative of 16, which is just 0. All right, That's the hardest part of the question. Okay, now if you look at this, we have all of these values except dy dt. So here you have options. You can rearrange this formula first so that it is dy dt equals, and then put your values in, our given values here, or you can put the values in now and then rearrange it. Either way, you're going to get a final answer that says dy over dt equals, and you'll get the number. So I'm going to rearrange this. So to rearrange it, we're going to go 3x squared dx dt plus 5 dx dt equals, you're going to move the 4y to the other side. So we get this. And then I'm simply going to divide both sides by 4y. So we divide by 4y, and we divide by 4y. These 4's cancel out, and we are left with dy dt equals the statement here, which is 3x squared dx dt plus 5 dx dt over 4y. Okay. You could factor out this the x dt, but it's not necessary. It's not necessarily necessary to factor that out, but you could. All right, let's plug in our values. Again, we have our known values on the board over here, and so we'll do it here. We're going to go 3 times 2 squared times 4 plus 5 times 4 over 4 times -1. And if we do that, and we do it all properly, we should get an answer of 17, I believe. -17. Right, 3 times 4, 8, 16. Yep, divided by -4. Okay, so there we go. There we have our answer, our derivative. We have found dy dt, which is again the derivative of y with respect to time. Okay, so this is just a general equation. The equation is given to you. It's a little bit of practice in taking the derivative implicitly with respect to time, implicitly differentiating both variables at the same time, and then solving for one of them. All right, we're going to go over to the other board. We're going to do an example that has a snowball melting. We'll do it. All right, here's example problem number 2. It simply says a snowball, a spherical snowball, is melting in such a way that its volume is decreasing at a rate of 1 centimeter cubed per minute. At what rate is the radius decreasing when the radius is 5 centimeters? An important aspect of related rate questions is that you are finding an instantaneous change, right? Because it's a rate of change. It's like an acceleration in cases where if a snowball's melting, right? The radius and the volume are changing at such a rate that rate of change is changing all the time. As it gets smaller, it's changing. So we have to pick a point. Okay, at this point, what is the rate of change of something? All right, so that's what's telling us when the volume is 5 centimeters. Okay, so the first thing we're going to do is we're going to recognize that as we read this question, we have volume decreasing and we have radius decreasing. So that means we need a formula. Okay, and the formula is something that relates volume and radius of a sphere, because that's our object as well, right? So if we were to draw a diagram, and really what our diagram is a ball. There it is. This ball has a radius. It's a snowball, but there it is. All right. Our formula is the volume of a sphere formula. So the volume of a sphere is V equals to 4/3 pi r cubed. All right. So there's our formula. Our formula relates volume and radius for a sphere. Now, what's given and what do we want to find? We are told that the volume is decreasing at a rate of 1 centimeter cubed per minute. Okay, that's a rate of change. We're going to call that dV, the derivative of volume, with respect to time. it is decreasing at a rate of -1 centimeter cubed per minute. Okay, so because it's giving us a rate of change is a derivative. Okay, all right. Then it tells us to find the r dt. It says find the rate at which the radius is changing. The r dt when r equals to 5. Okay, so we've now written down what we have, and we have written down what we need to find. We have our formula. Once we have this step, now all we need to do is take the derivative. Okay, we have a formula that has volume and radius, and only volume and radius, which is important as we get to some other examples. Let's take the derivative. The derivative of v with respect to time is simply dv dt. Okay. The derivative of 4/3 pi r cubed, keep in mind 4/3 pi is just a number, it's a constant, r cubed, so when we differentiate we're going to multiply the 3 out front, which will give us 4 pi times r squared, reduce the exponent by 1, and then the derivative of r with respect to time is dr dt. All right, now we're ready to solve it. We have this information, we have our formula, we are going to solve it, so we're going to go -1 equals 4 pi times 5 squared times dr dt, and if we solve for dr dt, we will get 0.003 centimeters per minute. Okay. As we do these questions, make sure you have units in your answer. I don't need to see the units in the work for these ones, but I do want to see units in your answer that give us an answer that makes sense to the question. So, what this is saying is, as the radius, or as the volume is decreasing at 1 centimeter cubed per minute, the radius is changing by 0.003 centimeters per minute. All right, it's just that easy. We're going to do 2 more examples. They'll get increasingly harder as we go along. And so let's do another example. All right, here's example number 2. Example number 2 is a bit more of a real world kind of problem, something that you wouldn't necessarily solve for this, but you could if you really wanted to. So what we have here is, here's the question. It says a ladder 20 feet long leans against a vertical building. The bottom of the ladder slides away from the building horizontally at a rate of 2 feet per second. Okay? So the bottom moving away 2 feet per second. How fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? All right, so I've started drawing our diagram on the board behind me. We have a building here, ground here, ladder in blue. The ladder is 20 feet long, so we're going to label that. Okay. The question tells us that this point of the ladder is sliding away at a rate of 2 feet per second. And so here's where we have to introduce some variables. We're not given any variables. So I'm going to call this distance x, and I'm going to call this distance y, right? X-axis, y-axis, if you want to think of it that way. That means that this distance x is changing, and we're going to call that dx dt. Okay? This y is sliding down, and we're going to call that dy dt. Okay, so we've introduced our variables, and this is what we have. Now again, we're going to write down what we have, what we need to find. And so again, we have dx dt is 2 feet per second, and the question is asking us to find dy dt, right? It didn't say dy dt, it said find how fast the ladder is sliding down the building. We called that dy dt, so we are saying now we're going to find dy dt when y equals to 12. All right. So once we have our diagram and we've written down our variables and our information that we're given and what we need to find, our next step is to find a formula that relates x and y together. And here's where you've got to use your imagination a little bit, because nothing's given, right? But when we look at this, one of the first things you should see, and the first thing I see, is we have a right angle triangle here. And we all know the formula for a right triangle, right? Thanks to Pythagoras' theorems, we're going to start with that. We have x squared plus y squared equals, and in this case, the hypotenuse is 20, so we're going to write 20 squared right off the bat. All right, once we have our formula, we can now differentiate it. Okay, and again, we're differentiating with respect to time, so we're implicitly differentiating both variables. So implicitly differentiating this, we're going to get 2x to the 1 dx dt plus 2y to the 1 dy dt, and 20 squared is just a constant, so the derivative of a constant is 0. All right, we're going to quickly solve this for dy dt because that is what we need to solve for, and we can do this pretty simply. We're going to go dy dt equals, we're going to subtract the 2x dx dt from both sides, and we're going to divide by 2y. The 2's can cancel out, so we're left with negative x dx dt over y. All right, let's start putting in values. If we start putting in values, we're going to run into a little bit of a problem here. Look what we know, okay? We want to find dy dt when y equals to 12. Great, okay? We know dx dt and we know y. But in our formula here now, for dy dt, we have this value of x. Okay? We don't know that value of x. Well, we do, but we haven't found it yet. So let's go find it. Because, again, we have a right triangle. When y equals to 12, x equals a particular value, right? And so to do that, we're going to just do a quick calculation here. We're just going to do it as sort of an aside here in between here. We're going to, again, go back to our formula. And we're going to put 12 in, and we're going to solve for x. Okay, so x squared plus 12 squared equals 20 squared. Subtract 12 squared from both sides, take the square root of both sides. Now we're going to get x equals 16. Okay, now again, when you take the square root of both sides, you're going to get positive or negative 16. But in this case, we know we want the positive because we're dealing with a physical distance. That will be positive 16. All right, now we can go back and we can finish our question. Okay, now we know what x equals. So we'll come back over here and I'm going to rewrite it. We're going to go dy dt. And we're going to use our formula. We have negative x was 16, dx dt is 2, y is 12. And we can either use fractions or we can use decimals. If we use fractions, it is negative 8/3 feet per second. If you would rather use decimals, it is 2.66 feet per second negative. Okay. Again, questions, answers need to make sense for the question. We are getting a negative value for the rate of change because the value is it's going down, right? So again, just like physics and everything else that we do, direction matters. Okay, this is going down, so we are getting a negative number to reflect that it is going down. Okay, all right, let's do another example. All right, so here's our next example. Let me read it to you again. I've got a diagram drawn on the board behind me. Let me read the question that goes with it. The question is, a water tank is to be built in the shape of a circular cone with a height of 5 meters and a diameter of 6 meters at the top. Water is being pumped into the tank at a rate of 1.6 meters cubed per minute. Find the rate at which the water level is rising when the water is 2 meters deep. All right, so first thing we're going to do, again, we've read the question, we understand that water is being pumped in. That is a volume that is going to be changing, okay, meters cubed per minute, and the height of this water is going to be rising, right? And because it is a cone and fans out, the water level rising is not going to be a constant. It's going to change. And so we want to find how fast the water is rising when the water level is 2 meters deep. So I've drawn a diagram. Here's our cone. I've drawn in a radius of 3 and a height of 5. And then in the middle here, I've got the water level. All right, we don't know what that water level is. We know that it will have a radius, and we know its height is 2, but we're not going to put that in yet. Okay, we're going to hang on. We're just going to leave it as h for now. all right? And that's important. Don't put constants in until you have to at the end, all right? Because 2 is not necessarily a constant, right? 2 is always changing, so don't put it in until we have to. Leave it as h until we get to a point where we want to put it in. All right, so we've got our information, we've written it down, we've written down what we have and what we need to find, and so now we need a formula. So because we need a formula that relates volume to radius and height, what we need to do is find that formula. So the volume of a cone like this is, should we get it right here? It's 1/3 pi r squared h. Okay. So again, pi r squared is the area of the top, the circle. Height is the height, and then because the cone is 1/3. If it was just a cylinder, pi r squared h is it, but it's a cone, it's 1/3 of that. All right, so now here's where it gets interesting. Here's where we have to think a little bit. If we look at this formula and we try to differentiate it, we're going to get a dv dt when we differentiate v. We're going to get a dr dt when we differentiate r, and we're going to get a dh dt when we differentiate the height. In our known and given information, we have dv dt and dh dt. There's no reference made to dr dt, and yet when we take the derivative of this, we will get a dr dt. So we can't do it the way it is. We have to find a way to eliminate this radius out of this equation. We need to write it in terms of the height. So that takes us back to this question here, all right? And I don't know if you can see it or not. Again, when you do more of these, you'll be able to see some of these things. But in this diagram, we have 2 similar triangles, all right? We have this big triangle that is 3 and 5 on the side lengths, and we have a smaller triangle that is r and h. Similar triangles, we can set up similar triangle ratios. So we can say that 3, write that here, 3 is to 5 as r is to h. Okay, now it's the r we want to eliminate out of that formula, and so we want to solve this equation for r, and so here r will equal to 3h over 5. Okay, this allows us to make a substitution into our volume formula over here. So we're going to go volume equals 1/3 pi 3h over 5 squared times h. We're going to simplify this real quick to make this happen. So we're going to do this. We're going to go 3 squared is 9 divided by 3. It's going to give us 3. That was hard work, okay? So we have 3 pi in the numerator, our denominator, and we have an h squared times an h, so an h cubed, and then in the denominator we have 5 squared, so over 25. Okay, so we have 3 pi over 25 times h cubed, and again we want to think of it that way because 3 pi over 25 is a constant, and the h is our variable. Okay, so again, just simplify this, square this, gives us 9 over 25 h squared. H squared times h is h cubed. The 9 over 3 becomes 3, and I left the 25 the way it is. All right, now we're ready to take the derivative. So derivative is dv dt equals to 9 pi over 25 h squared. So we multiplied the 3 out front. 3 times 3 is 9. Reduce the exponent by 1. Multiply by the derivative of h, which is dh dt. All right, now we're good to go now. Let's solve the problem. dv dt is 1.6. 9 pi over 25, constant. H is 2, right? We want to find it when h equal to 2 squared times dh dt. Solve for dh dt by dividing both sides by this 9 pi over 25 times 4. And the answer you get will be dh dt, the height is changing at a rate of 0.4 meters per minute. Okay, so keys to this question again, following the steps. We read the question carefully, we understand what the question is saying. Draw a diagram, introduce some variables, write down what we know, what we need to find. Then we need the formula that relates those things together for our shape. Here in this one we recognize that there were too many variables. We didn't know enough information in our knowns, so we had to go back here and try to eliminate a variable with some of the information given in the question. Once we had our simplified formula here, we took the derivative, and put in our values and got the answer. All right, so again, follow the steps, go through the steps. Again, each question is going to be slightly different. It's going to require you to be creative, to find equations, to find ways to get the right variables in the equations, and then solve. Okay, so these are not simple questions. They are questions that require you to be creative and require you to persevere through them until you get to a point where you can get it. We're going to do one more example, and then you can look at the assignment that will be on Connect. Okay, here's our last example. This is a bit of a tricky one again, but here I'll read it to you, and then we'll see if we can solve it. It says, a spotlight on the ground shines on a wall 10 meters away. A man, 2 meters tall, walks from the spotlight toward the wall at a speed of 1.2 meters per second. How fast is his shadow on the wall decreasing when he is 3 meters from the wall? All right, so I've started drawing our diagram. So what we have here is we have on the ground here, we have a spotlight that's shining up. That creates a shadow on the wall. That'll be that tall. This man is 2 meters tall. Okay, and the spotlight is 10 meters from the wall. Okay, so start with that information. Now this man is walking toward the wall. That way. Okay, at a rate, and tells us that rate. It tells us that he is walking at 1.2 meters per second. As he walks towards the wall, this shadow will get smaller. Right? And that's what we want to find. We want to find the rate at which the shadow will get smaller. So that's the question. Okay, this is what's happening, and we can all sort of picture this in our heads, that if we had a spotlight on the ground shining, we walked toward the wall, away from the spotlight, the shadow on the wall would decrease. The question is, by what rate? All right, so we need to introduce some variables. So here's what we're going to do. Now, this distance here between the spotlight and the man is what's changing at a rate. Okay, and so we need to set that up as x. Or y, whatever variable you want. I'm going to use x again because it's horizontal and the x-axis is horizontal. And that means that this is changing dx dt at our rate that was given in the question of 1.2 meters per second. Okay, so that's changing there. This vertical one that's changing, I'm going to call the vertical axis y again. And then this changing shadow height will be dy dt. All right, so this gives us our information. The question again is to find dy dt when he is 3 meters from the wall. So if he is 3 meters from the wall, what does x equal? I hope you can do 10 minus 3. All right, so we want to find it when he's 3 meters from the wall. In other words, we want to find it when x equals to 7. All right, so here's our diagram. Now here's where we have to get creative and we have to think about this a little bit to make ssure we get the equation right. So now that's the next step, is finding the equation that relates x and y together. And again, I'm hoping that you can see similar triangles in this question. All right, we have a big triangle formed by the wall and the ground to the spotlight. We have a smaller triangle that is the man, the ground to the spotlight. All right, and again, when we have similar triangles, we can set up similar triangle ratios. So let's do that, okay? So if we set up our similar triangle ratios, we have our y okay, the vertical side over the horizontal side equals the smaller triangle, the vertical side, over the horizontal side. There we go. There's our formula. Y over 10 equals 2 over x. You can take the derivative of this the way it is, but because it's such a simple equation, it's way easier to do this if we solve for y and get this. Okay. And again, I would even make this then 20x to the negative 1. And now I'll take the derivative. So the derivative of y with respect to time is dy dt. Over here, we're going to multiply by negative 1, reduce the exponent by 1, and then take the derivative of x with respect to time. And of course, if we simplify that, let's just move that x to the negative 2 back to the denominator, and we get this. All right, so we have dy dt equals negative 20 over x squared, dx dt. We know what x is, we know what dx dt is, so we can substitute into this equation and get the answer. So negative 20 over x, which was 7 squared, times dx dt, which is our 1.2, and punch that into our calculators and we will get an answer as a fraction that is negative 24 over 49. And that would be meters per second. A decimal is perfectly fine. 24. It would be approximately 0.49 meters per second. Okay, and that's totally fine. Either way, fractions or decimals are fine. The answers that you'll see in most textbooks will be the fraction answers because, again, in math, exact answers are important. And if we do this as a decimal, it's 0.489795, blah, 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 and on and on. No longer an exact answer. So fractions are better, and answers in the textbooks will be fractions. If you want to do it as a decimal, that's fine. Just make the conversion. All right. You're going to get a bunch of questions now. I think there are 16 or 17 questions, and over the next couple of days, I want you to work on them. Okay, we're not going to do another lesson this week, so we have all the way till next Tuesday before we'll see another lesson. But over the next few days, what I'm going to do is every day I'm going to do a few of the questions in the assignment. Okay, just as solutions. So you can come in, and once you've done a few questions, you can come and check which solutions that I have put online, and you can check your solution with my solution. You will have the answers to the questions on the assignment, but if you're not getting them and you want to see the solutions, check in for a video on the solutions to these exercises. And again, some of these questions are tricky, okay? Because again, no two question is the same, okay? There's all kinds of variations with this particular question that you can get. Okay, the man walking towards the wall, away from the wall, what's given in terms of when we're supposed to find it. So be creative, think, again, follow the steps, and as we go through these, hopefully we'll get better at them. It is our last section in this unit of applications on derivatives. So we're going to spend some time with related rates the rest of this week and into early next week. Then we'll start doing some review of all things applications, velocity, acceleration, optimization, and related rates. And then we'll have an assessment of some point after that before we get into our final unit, getting into integration. All right, if you have any questions, make sure you email me, and I'll be happy to respond to them. And have a great day, and we will see you tomorrow with some solutions. Have a good day.